south of Iceland, there's a patch of ocean roughly the size of a small continent that is getting colder, not warmer. Colder in a world where nearly every other stretch of ocean on Earth is heating up. Scientists have a name for it, the cold blob. And in the summer of 2026, while France recorded its hottest temperature ever measured, the cold patch of water sat quietly. In the North Atlantic, doing something researchers say is directly connected to the heat baking the rest of the continent. That's the paradox nobody can quite look away from. One patch of ocean refuses to warm, while the land right next to it burns at record levels. And scientists studying both pieces of this puzzle are increasingly convinced they're not separate stories. They're the same story. Let's set the stage properly, because the details here matter more than the shock value. This isn't a claim that Europe's climate has broken beyond repair overnight. What we're going to walk through is what actually happened, what the research says is driving it, and why the combination of a cooling ocean patch and a record-breaking heat event has scientists paying closer attention than they have in years. Start with the heat, because it's the part that made headlines first. In June of 2026, Western and Central Europe was gripped by an extraordinary heat wave. France logged its highest temperature since national records. It began in 1947, with the mercury hitting 44.3 degrees Celsius. Towns across France, Spain, the United Kingdom, and the Netherlands recorded readings far above anything considered normal for the season. The mechanism behind that heat has a name too. Meteorologists call it an omega block, named because the shape it traces across the jet stream resembles the uppercase Greek letter omega. Under normal conditions, the jet stream, a fast-moving ribbon of high-altitude air, pushes weather systems from west to east across the continent, so no single pattern sits in place for long. Now understand what happens when that flow breaks down. During an omega block, a large area of high pressure becomes sandwiched between two zones of low pressure, and the jet stream bends dramatically around it instead of pushing through. Rather than moving on after a day or two, the same weather conditions can sit locked over the same geography for days, sometimes weeks at a time. That's why this heat wave didn't behave like a normal hot spell. It didn't pass through. It parked itself over Western Europe and refused to leave, trapping a dome of hot, dry air that had originally been pulled north from the Sahara. Most omega blocks last somewhere between 3 and 10 days before the atmosphere finally breaks the pattern apart. This one persisted well beyond that typical window, and researchers tracking its evolution watched the hottest core shift eastward over time, moving from Iberia and France toward Germany, Poland, and the Alpine region as the block held its shape. But that's not even the strangest part of the story. While that heat dome baked the continent, researchers studying ocean temperatures south of Iceland and Greenland were tracking something that shouldn't be happening at all in a warming world. A stubborn patch of cold water, resisting the global warming trend almost entirely on its own. Read that again, slowly. Nearly every ocean basin on the planet has been warming for decades. This one patch, sitting directly south of Greenland and Iceland, has been doing the opposite. Scientists first started documenting this cold anomaly years ago, watching sea surface. Temperatures in this specific region diverged from the surrounding North Atlantic, even as global ocean heat content kept climbing overall. What makes it worth tracking closely isn't just the anomaly itself, but its remarkable persistence, showing up year after year in satellite and buoy data, rather than fading as a one-off fluctuation. Here's where the two mysteries start to. At the University of Bremen, who has studied this cold blob extensively, have found that this patch of unusually cold water can actively reshape the jet stream's path over Europe. Instead of flowing normally across the continent, the jet stream bends northward and flows around Europe rather than through it, allowing a heat dome to settle in underneath. Now here's where it gets disturbing. The cold blob isn't just an isolated ocean quirk. Scientists increasingly view it as a visible surface symptom of something much larger happening beneath the water, a weakening of the Atlantic meridional overturning circulation, the vast system of ocean currents that carries warm water north from the tropics and helps regulate climate across the entire northern hemisphere. Let that land for a second. The same current system tied to sudden cooling in one patch of ocean is also tied to the very heat wave pattern currently breaking European temperature records. One weakening system, producing what looks, on the surface, like two completely contradictory outcomes. Scientists studying this connection describe it as counterintuitive, precisely because most people assume a warming planet should produce uniformly warmer conditions everywhere, all the time. The reality, as this pattern shows, is that warming can destabilize the very systems that used to keep regional climates predictable, producing sharper extremes in both directions, rather than a simple, steady rise. To understand why a weakening current can cause both extreme cooling and extreme heat at the same time, you have to understand what this circulation actually does for the region. The Atlantic meridional overturning circulation works like a conveyor belt, carrying warm surface water north while cold, dense water sinks and flows back south deep beneath the surface. That constant motion is part of what keeps Northern Europe's climate milder than its latitude would otherwise suggest. When that circulation slows down, less warm water reaches the North Atlantic near Iceland and Greenland, which is exactly the kind of local cooling researchers have measured in the cold blob. At the same time, a weakened circulation changes atmospheric pressure patterns downstream, patterns that appear to be steering the jet stream into the exact blocking configuration that trapped this summer's heat over Western Europe. Think of it less like a single switch and more like a domino chain running underwater and through the atmosphere at once. The current slows, the surface cools, the temperature contrast between that cold patch and the surrounding warmer water shifts local pressure systems. And that pressure shift nudges the jet stream into exactly the kind of bent, stalled pattern an omega block requires to form and hold. That's the uncomfortable core of this story. A slowing ocean current isn't just a distant, abstract climate statistic. It may be actively reshaping the day-to-day weather patterns hitting European cities right now in ways that produce both a freezing ocean anomaly and a record-shattering heat wave from the exact same underlying cause. If you've made it this far, you're clearly the kind of viewer who wants to understand what's actually driving the headlines instead of just reacting to them. That's exactly why this channel exists, so if that's you, go ahead and subscribe for more of these deep dives. Now let's be precise about what science can and can't say here, because that distinction matters. Researchers have not reached a firm consensus on whether climate change is making omega blocks themselves more frequent. What is established is that when these blocking patterns do occur, a warmer baseline climate is making the heat they trap significantly more dangerous than it would have been decades ago. Similarly, scientists studying the cold blob are careful about their language. A recent study reinforced concerns that the pattern could signal a weakening AMOC. But researchers stop short of declaring the current has already collapsed. What they will say clearly is that the trend lines are consistent, and consistent enough to take seriously. That kind of careful, measured language is exactly what you should expect from credible climate research, and it's worth noticing when a claim doesn't come with that same caution attached. Extraordinary claims about sudden climate collapse tend to travel faster online than the nuanced, peer-reviewed research they're loosely based on, which is part of why going back to primary sources matters as much as it does. Here's why that distinction actually matters for you. This isn't a doomsday countdown with an exact date attached. It's a pattern scientists are watching closely because the pieces keep lining up the same way year after year, and because the stakes of being wrong in either direction are enormous. So what does this mean for the world beyond this one summer? Research on comparable. Recent heat waves has found that events of this intensity would be far rarer without the influence of human-caused greenhouse gas emissions, meaning this isn't simply an unlucky season. It's a preview of a pattern likely to repeat. A weakening AMOC carries its own separate set of long-term risks beyond a single hot summer. Scientists warn that continued weakening could eventually lead to harsher winters across northern Europe, even as the rest of the planet keeps warming, disrupting agriculture, energy demand, and infrastructure planning that has assumed a relatively stable regional climate for generations. That's a difficult idea to hold in your head at the same time as record summer heat, but both outcomes stem from the same weakening current. A slower AMOC means less consistent heat transport north, which can mean colder, harsher winters in exactly the same decades that summers grow more extreme, stretching the range of conditions any given region has to prepare for on both ends of the calendar. Energy grids built around predictable seasonal demand patterns are already starting to feel this strain. Utilities across parts of Europe have reported unusual spikes in both summer cooling demand and winter heating demand within the same year, a combination that older infrastructure planning models simply weren't designed to anticipate. So what can you actually do with this there regularly? Start treating extended heat events as a recurring seasonal risk rather than a rare anomaly, and know your region's cooling centers and heat safety protocols before the next omega block settles in. Pay attention to how local infrastructure is adapting. Cities across France and Germany have started updating building codes and public cooling strategies specifically because of events like this one. And knowing what resources exist near you before an emergency starts is far more useful than scrambling once temperatures spike. If you're traveling to Europe during summer months going forward, build flexibility into your plans rather than assuming historical seasonal averages still apply. Check extended, forecasts closer to your travel dates than you might have in the past, since blocking patterns like this one can develop and persist with less advance warning than typical seasonal weather. For anyone living in a region affected by these blocking events, basic heat safety habits matter more than people often assume. Stay hydrated well before you feel thirsty. Avoid strenuous outdoor activity during peak afternoon hours, and check in on elderly neighbors or relatives, since heat-related health risks climb sharply for older populations during prolonged events like this one. If you're following the bigger picture, keep an eye on AMOS monitoring research specifically, since it's now one of the clearest indicators scientists have for how Europe's weather patterns may continue shifting in the coming years. It's not the flashiest number in climate science, but it may end up being one of the most consequential. Researchers currently track this circulation through a mix of moored ocean sensors, satellite altimetry, and long-term temperature records, and several major monitoring programs publish updated readings on a regular basis for anyone interested in following the raw data rather than waiting for the next headline to summarize it. Before you go, tell us in the comments whether you noticed this summer's heat, where you are, because this pattern reached far beyond the headlines most outlets focused on. And if you want to keep tracking how this story develops, stay subscribed, because we'll be watching the data as closely as the scientists are. This is the kind of story that unfolds slowly, one monitoring update and one research paper at a time, rather than announcing itself with a single dramatic headline. That slow pace is exactly why it's easy to miss, and exactly why it deserves closer attention than it usually gets. Let's close where we started. A patch of ocean quietly refusing to warm while the world around it heats up, and a heat dome sitting locked over Europe for weeks at a time. Two events that look like opposites. One underlying cause that scientists cannot look away from,